then it goes down. Now we have half more people, okay. But yeah. What happened so far? So we had some introduction, then we had some talk, some discussion, I would say, about importance of the strong field considerations in different components. And then you spent 4 hours on Friday. So Ron was trying, I understood, to remind some of you, maybe some of you just got some new information about the electric fields. What types can be in the high voltage components, capacitive, resistive, how to control these things. More or less, we just touched this. Maybe today will be some addition to that. So what will happen next? 3 kind of blocks of lectures. First, today we will consider how strong electric fields affects gases. How the breakdown happens, how the current flows, why, and what type of visual appearances this phenomenon actually take. Next, on Friday, there will be 2 lectures considering solid liquid insulation and practical applications, like transformers especially. There will be one more talking about that, about the basics, and then there will be Andreas Kukler talking about transformer insulation design, or let's take it oil response. And then next week, Friday next week, will be solid materials, about cable technology and solid insulation. So now we start with gases. What actually happens if we expose gas to strong electric field? Just to remind you where we are in these learning objectives. So we look on this phenomena leading to the failure of different type of apparatuses, identifying insulating materials used in high voltage technology, characterize advantage, disadvantage. We already look on its electric field related things, so it's already markets kind of done. Process knowledge on allowable working electric stresses. Methods for controlling the electric field, we already talked about that. Physical mechanisms responsible for various types of electric discharges and gases. So this especially topic for today. Yeah, how this performance of different materials depends on temperature, humidity, pressure, mechanisms of electric conduction, how the current flows, that's what I just said, and some environmental concerns, what are the trends today in the gas insulation systems. Okay, so when we apply strong electric field to different electrode systems, let's take it in this way, more simplified, what we can observe. These kind of things, something similar you eventually will see in the lab, not really on this scale, because this is taken with a kind of zooming camera in a very high resolution camera, where you have this corona type of region from one metallic electrode, and then one of these branches eventually converted to thin filamentary channels, which actually creates breakdown paths. So this is called corona region, this is called streamer discharge. Filamentary type of channels, plasma channels, we call these streamer discharges. This is typical corona phenomena, where you have sharp edge somewhere, here maybe some ground electrode somewhere, whatever. The fact is that there is a potential difference applied. This creates strong field with very low field factor, right? So then we have this type of channels just propagating. This is not a breakdown. This is breakdown. It's a phenomenon. We will especially look at this point, because very often people mix the discharge and breakdown. This is different things. Yeah, this is also something which we can see in practice. Something similar to this, sharp edge somewhere, then there is some kind of ground, whatever type it is, but then we have a dielectric plate placed in between. So what actually happens, this plate creates some obstacles for these plasma channels to propagate. So they just instead take the path along the dielectric plate, bringing charges to it actually. And what actually happens, if you can see this, I think you can, there are small kind of filamentary discharges which are kind of distributed more or less evenly below the plate. That means that the plate is charged, create charges, and then there is the field which appears between the charged plate, which appears to be under floating potential in some sense, and the fixed grounded electrode here. So that's a second type, the second short gap, which also creates some discharges here. So it's quite complex phenomenon. Also this type of things. This is post breakdown event. So what happens, you have this type of things, okay? If it's high pressure, you will have it in a filamentary form. If you reduce the pressure, 1 kilopascal, 100 pascal, 10 pascal, 1 pascal. You see what happens, it becomes more and more diffusive. Just, yeah, we will discover today eventually the reasons for that. And then it becomes like this. This is more typical, I would say. So we have electrodes, some electrode regions with some voltage drops, and then we have very long, what is called positive column. It's in general, this phenomenon is called glow discharge. That's what happened in these lamps. So in these lamps, we have typically the mixture of neon and helium eventually. It can be different. If you see this reclam things, so they have different colors, and it's all about mixture of gases. But the principle is the same. Sorry. Here there is kind of, yeah, if you look closer, really, behind this small box in the box you have very small winding. When you switch it on, it creates a pulse, which actually breaks down the gap, and then the positive column starts to glow, and that brings the light. So these kind of things are used for lighting in many different applications. What is common for this? It's called non-thermal discharges. That means that the temperature of electrons, in terms of energy, if we convert this to temperature, is high here, but the temperature of neutral particles is still kind of close to room temperature. So that's the difference. It's also called sometimes non-equilibrium plasma. So it's there is temperature difference between different components in this plasma channels. There could be thermal discharges, which is typically post-breakdown phenomena. Starting from this scale, it's a spark plug in the combustion engine or diesel engine. There will be different constructions of this as well. But the point is that here you have the insulator. It's actually bushing, small bushing. Here it's connected to the coil, which produces normal current, maybe up to 20 kilowatt or something, pulses. Then it goes to this. This is connected to the body of the car. So, and then you have this millimeter maybe scale gap, but intensive sparks appear to burn the fuel. So this is all of the thermal discharges. The temperature of neutral particles is really high here, and that's why it gives the ignition to the fuel and air mixture. This you saw already in the video. This is arc discharge. So this is also thermal plasma. And lighting finally, which can be kilometers long, these channels, they carry currents up to hundreds of kiloamps, very concentrated, and here you have the temperature of neutral particles, like thousands of Kelvin, several thousands typically. So you see different scales, but in principle they have something in common. Of course the mechanisms are very different, but still it belongs to the class of thermal discharges. Okay, so this is classical picture. You can find in many textbooks what happens if you apply voltage to a parallel plate system, two electrodes, uniform field, and then you measure the current. And you start measuring the current at very, very low values if you have sensitive enough device. So what you will measure first, there will be a rise of the current, which is kind of ohmic region. So what this says, that you have some charged particles already in the volume between the electrodes, which are exposed to external field, and they start moving, they're producing a current, right? At some point, you reach the level where all the particles which are present between the charged particles between the electrodes, they are already consumed in a way. So it's saturation region. But the voltage and at the same time the electric field, it continues to grow. We will see later that the particles acquire some energy from electrostatic field, and they move faster and faster. At some point, their energy becomes high enough to collide with neutral particle and release new electrons. This is called impact ionization phenomenon. We will talk about that. So we just creating kind of avalanche. So it hits, release new electron. This new electron start accelerating. The old one is still there, also accelerating. Each of them collide again, and that creates chain reaction. So that leads to increased current, which is called dark discharge, or Thomson discharge sometimes. You might find this. And then it's rising, rising, rising until you reach the point which is the breakdown. At this point, the discharge becomes self-sustaining in a way. Due to different mechanisms, we will talk about that, either supplying secondary electrons from the cathode or some mechanisms which provide them in the volume of the gas. These chain reactions become self-sustaining, and then it's somehow not really dependent on the external field so much. We only need the field to sustain the propagation of the plasma channel. And then depending on the external impedance of the external circuit, the power supply, the voltage drops, the current still rising. And then it becomes constant, more or less at very low voltage, lower than breakdown voltage, right? And that's what happened here. So then you have quite long range in terms of current, where you can have this glow type of discharge. It can be normal, abnormal, it's different type of classification, let's say, and it depends actually what is the current density of the cathode. If the glow occupies the entire surface, of the cathode, it starts growing because the current is growing, right? So basically, it just after the glow appears, it just concentrated, but then it becomes rising in the area covered on the cathode side because it should supply the higher current, and then at some point it covers the entire area, and then it becomes abnormal in a way, and then we have again need some voltage to support this, and this is already transitioned to an arc discharge. In the arc discharge, you have extremely low voltage compared to the breakdown level, but extremely high current. Because what comes in play in the arc discharge is thermal ionization. The temperature of neutral particles becomes high enough to ionize them when they collide with each other. So not only electron impact, but now it's thermal ionization. So neutrals collides with neutrals. So for this, the temperature should be really high in the plasma, and in the arc is normally from 5 to 10,000 degrees. That's what is needed for thermal ionization. Okay, that's the whole story more or less. But let's look here. That's where all this starts. And the question is where these initial particles charged particles come from, which supply this extremely low current. So, yeah, they appear due to cosmic radiation, natural factors, cosmic rays which appear in Earth's atmosphere, natural radioactivity. Usually this is one of the important factors in the areas where there are a lot of rocks, and that's actually typical for Sweden. And in Sweden, there is, if you live in some area where you have rocks, what is typical, there is control of radon level. Perhaps you have this in your whatever place you live. Here is Stadsred. It's kind of must, not always fulfilled, but in principle, the rules are that there are special people who going around, especially in the low-level regions, like in cellars or something, and measure the radon concentration. Because these rocks, they create alpha particles, which ionize the gas, and then these chemical reactions lead to production of radon, which is a radioactive gas, and it's just heavy. It just sits in the low-level areas. So, but that's also part of one of the sources of that's what we can give. One of the sources of charges. The concentration which appears due to this is extremely low. So we have a rate of burst under normal conditions is about 1/10 this level ionic pairs per cubic centimeter per second. So if you take cubic centimeter in this room per second, you have about this number of events which produce charged species, electrons specifically. So the background density due to these processes is about 1,000 ionic pairs per cubic centimeter, which is extremely low. If you compare with the gas density, just under normal conditions, maybe you know this from the physics course, ideal gas. The pressure of the gas, let's take it in another way. Not the pressure, but the concentration of the gas. Is the pressure Pascal divided by kT, right? K is the Boltzmann constant. So if you, we will have this exercise today, but anyway, if you take typical pressure, 750 millimeter of mercury column, and then multiply it with 133.3, which is the conversion to Pascal, and divide it with 138 10 to minus 18, I think, or something. That's I have to check. And multiply with 293. So this is question Kelvin. So basically, after just estimating this, you will get something like 10 to 219. Neutral particles per cubic centimeter. So in 1 cubic centimeter, you have something on 10 to 19 neutrals. And we are talking about 10 to 3, 1000 among those 10 to 19 electrons. But even this gives rise to all these things, because of this intensive multiplication which appear in the strong field region, and then it comes to all this phenomena. Yeah. Another thing, if you put in motion all this 10 to 3, just in the low level field, somewhere here, so then you will arrive to this current depth. So that's exactly what is in this region. And if we put in motion all this 1000 ionic pairs, without giving rise to new ones, so then that's why the saturation happens. So multiplication comes later when the energy becomes high enough. Yeah, and if we just take this and divide with the field level here, so current density divided by the electric field, you will get the conductivity, right? And this conductivity is on the level of some 10 to minus 13 Siemens per meter. So that makes it very good insulator, air or any other gas. It may be higher or lower, but still is this level. Very good insulator at low field region until this happens. Then it becomes very good conductor anyway. So that's what the breakdown is about. Okay. Yeah. Here you stop multiplications of charges because of the field level. What happens actually? There are always collisions, right? It's a gas. It's not a solid where all the charges, or actually the neutrals, they are sitting in the crystalline lattice. They are not actually freely moving. In a gas, it's free motion, right? And particles always collide with each other. What type of collisions can be? Can be elastic collision or non-elastic. What is elastic? It's momentum transfer. If you play billiard, you know what it is. So two spheres collide with each other. Depending on the mass, they transfer the impulse. Mass multiplied with the velocity. But if they transfer the energy, if they are capable of, if they are flexible, not solid spheres, then they deform, right? They change internal energy. That is called non-elastic collisions. Okay. So let's look a bit closer to typical parameters which appear in this when particles collide. Let's consider just some particle target and then some flux of other particles which just moves against this one and eventually collides. So if we consider like density of targets, these ones, NT per cubic centimeter, And then relative speed between this and this, which is W, meter per second, or centimeter per second. So, number of impacts. How many events happened during 1 second? This is called collision frequency. So it of course depends on the number of targets, right? In the unit of volume, the velocity, and something that is called cross-section. Cross-section is pure geometrical parameter. And this is kind of quite clear. If you have a particle here, target, and then you have another particle which just moving against this one. If it goes this way, it always will be collision, right? They will collide. If it goes this way, there will be collision still, right? But if it goes like that, no collision happens. So the collision only possible in this cross section. So that's what is called cross section for impact. By the way, I'm wrong. It's not like this. It's actually should account for the radius of that one. Like this. If these are two molecules, they should be double of the diameter of the molecule, right? We will have a short, small exercise for this. Okay? Effective collision frequency is the average of impacts of particular type. It can be elastic, non-elastic, different kind of collisions, which are made in 1 second by a particle of type 1 moving in the gas of particles type 2. Okay? With certain density. In case of electrons and atoms or molecules, you can write like that. The frequency of collisions which electron make in the neutral gas depends on the gas density, velocity of the electrons, and the collision cross-section, which is also dependent on the energy of the electrons. So quite simple definition, and this is widely used in the studying of gas dynamics, plasma chemistry, and then this kind of things. From this frequency, we can get mean time between collisions. It's just inverse. What this means, it's time when the particle experiences one collision, it's going perhaps, if it just goes this way, it then goes being reflected from that one. This is heavy, so this is not, and then it meets another one somewhere, another time. So time, which takes between these two events, this is called mean time between collisions. And it's kind of quite clear that it depends on the gas density, right? Because the gas density is more molecules per unit of volume. So this will be shorter, and the frequency, collision frequency will be higher, right? Going to this. Okay? And from here comes the very important parameter, which we call free path. It's a distance which this particle passes on between the collisions. Why this is important? Because for electrons, for example, the higher is the free path, the more energy it can get, right? From the field. Okay, questions? Sometimes it's kind of tricky to understand. Just don't hesitate to ask if something unclear. Here's the example. So estimate magnitudes. Here's just estimations of values. So the gas dynamic cross-section, collision frequency, time between collisions means free path. Normal pressure, normal temperature, typical diameter of gas molecules, 10 to minus 8 centimeters, considered like solid spheres. Chaotic thermal velocity is 10 to 5. No field, it's just chaotic motion. So that's what I was trying to draw here. Two particles of the same type, they collide, and collision cross-section is just like that, right? An elastic collision between two atoms, molecules in a gas is possible only if their centers are located with the distance, which is defined like double of the, like the diameter of the molecular distance, double radius. So then, if we put these things here, we will get some 10 to minus 16 centimeters squared. Oh, sorry. Yeah, centimeters squared. So it's extremely low values. It's kind of can be expected on the microscopic level. So what happens if we try to estimate the collision frequency? So we know cross-section now. What we need to get the density of the molecules in the unit volume and multiply with the velocity of chaotic motion. Yeah, that's what I was trying to again write there. Pressure conversion factor to torr, to Pascal. Torr, by the way, is a unit of pressure which is equivalent to millimeters of mercury core. So very often used in gas discharge physics historically. Then you have this, yeah, 10 to minus 23, not 18. I just mixed the dimensionality here. So they should be minus 23. Yeah, and then you have room temperature. So after all, you will get something like that. So 10 to 19 particles per cubic centimeter, multiplied with the cross section, which is this, gives us already 10 to 3, and multiplied with the velocity, so it will give us 10 to 8, roughly 10 to 9. So roughly that's 1 billion, right? 1 billion collisions per second happens in 1 cubic centimeter in this room. 1 cubic centimeter. Molecules collide with such frequency. So, and if you convert it to time between collisions, that will be nanosecond. So each nanosecond collision happens in 1 cubic centimeter with this condition. And finally, the mean free path. How long distance molecules travel between collisions. So this is just like inverse of the density multiplied with the cross section, and it becomes 10 to 19, 10 to minus 16, 10 to minus 4 centimeters. So that means it's 10 to minus, it's like 100 nanometers, right? Something like that. So extremely short distances. It's just under normal conditions, neutral particles. These are typical orders of magnitude, just for orientation, what we are talking about. Now we talk about electrons. These guys, they interact with the field, right? So they get the energy from the field. The rift, then we should consider the rift. So far we were talking about thermal motion. It's chaotic motion. It's just, equal probability to any direction because of the temperature. But rift is different story because the rift is directional motion. So you have certain direction of the electric field, you have the particles which experience electrostatic force, and they are pushed to move just in certain direction. At the same time, they continue this chaotic motion. So it's two types of two types of motion which are superimposed, let's say. So drift is considered just a very simple estimation here, just in the mechanical sense. You have second Newton law. Mass multiplied with acceleration, it gives you the force, right? So the force is electrostatic force, the charge multiplied with the field strength, and here you have the kinetic. The kinetic is just a product of mass and acceleration. So if you solve this, this is the time derivative. So if you solve this, you will get the velocity of the particle as a function of time. This is the force divided by mass, multiplied with time, and this is the initial condition for this differential equation, which is chaotic velocity. Okay? So now one should think that, okay, it's all kind of probabilistic things, because this is kind of have the same probability in any direction. This is unidirectional. So we have to talk about overaging. There is no other way, because otherwise we should consider this for each individual electron, which doesn't make much sense. So then we do overaging, mean drift velocity. Then we overage this, and this gives us again this ratio here, and then it's overage time between collisions, which actually result in the overage collision frequency. So then we have this overage collision frequency is defined via the density of the gas, velocity, and transport cross-section, which is the function of the velocity. So this is taken in the statistical sense. It's called effective collision frequency. So transport cross-section, it's a different from collision cross-section, because this is just hydrodynamic cross-section, but transport cross-section is just collisions which happen on the direction of the drift. So these are different things. So these all are, this gas kinetic, gas dynamic cross-section, transport cross-section, ionization cross-section, it's a subject of plasma chemistry, and there are books on that, and it's tables, like 100 lines for different compositions, different field levels. You have different people measure these things actually. Okay? Yeah, drift and chaotic motions are different things. And then it comes from this definition, it comes to something which we call mobility. It's very often used for different estimations. So it's a drift velocity from here. Yeah, defined from this expression here. So if we take this separately, then it will be defined as the mobility. So what is this actually? The mobility, it's a charge of the particle divided by its mass. It's kind of fundamental physical constant for different type of particles. But then it accounts for this effective collision frequency. So that's what defines the mobility. Looking just on this definition, one can think, okay, we have electrons and ions. Normally what happens when electrons ionize neutral particles, so they create electron and ion. The mass of the electron is very small compared to ion, right? So, and that gives, for the mobility, the fact that ionic mobility is much lower than electronic mobility. The factor is about 1000. So basically, in the measurements, one can see that, from the measurements, one can see that electrons are just much faster. Ions are heavy and they drift very slowly. So when you measure the currents in the gas discharge, and when you do these measurements for this electron avalanche process, I will tell more about that. Then you see two peaks, very sharp peak appear just after voltage application. This responds to electrons because they move very fast. And then after some time you have the peak of ions because they are very slow. They appear later after you apply the voltage. So just these few considerations from the motion of electrons in the gas. What I want to show you here is how people actually define this mobility from the experiments. In the experiments, people do measurements for different conditions. And what is, you can find in the textbooks, usually in the tables what is presented is reduced electron mobility. Basically it means that it's an absolute mobility multiplied with the pressure. In this way people try to generalize the results. Here is again the example, to see what is the absolute mobility for normal conditions, normal pressure. So we take just one tabulated value, measure it, divide with the pressure, and after all, we get this, about 600, 700 centimeters squared per volt second. This is typical values for electrons. And if you multiply this with the electric field close to breakdown, that's what question is about, calculate the velocity of electrons corresponding to pre-breakdown stage. So at breakdown in air, the field is roughly 30 kilowatt per centimeter. So we take this mobility, multiply with this field, and then we get this, or basically 200 kilometers per second. So the electrons move with this velocity, 200 kilometers per second, close to the breakdown. So it's not like the speed of light, but it's quite impressive. It's 200 kilometers per second. That's a drift velocity. Terminal velocity can be even higher. And then the question, what is the energy which electrons can get from the field when their mobility is like this? Okay, find energy gained by electron in the field 10 kilowatt per centimeter and close to breakdown. So that means that we have two values. We have this voltage current characteristic, ohmic region, then it goes to saturation, and then it starts multiplying, and here we have the breakdown. So here, let's say it's the field about 30 kilowatt per centimeter and 10 kilowatt per centimeter somewhere here. What happens in the saturation region? What happens close to the breakdown? So we got already free pass like 10 to minus 4 centimeters under normal conditions. The energy is just like that. The charge multiplied with the field strength and free pass. So very simple. Just multiplying these two values and 1.6 10 to minus 19 coulomb, which is the charge of the electron. So this gives us 1 electron volt. So somewhere here, electrons moving with the in the field have the overage energy about 1 electron when it comes to breakdown, the field is higher 3 times, and the energy is about 3. Okay? It's average values. One should remember this always, because in reality, we have the distribution of energy, and electron distribution function, that's what it's called. The energy and the number of electrons is usually like this. So basically, ionization is produced by these guys having high energy. This 3 electron volts is just an average of all this for the entire distribution, because we did the averaging for the cryptons, remember. So don't be confused with that, because then next what we will consider is the ionization threshold for different molecules, that it will be much higher than this one. That's important to remember, that when we estimate the energy this way, it's just an average. Okay? Okay, let's take a break, and then we'll consider how the ionization happens.